So the topic of my presentation is about the adversarial training for few-shot event detection, and uh, the contents are as follows. First, some background information about this research, and the second, the main work we have done and the innovation in this paper. And the third part is the experiment results, and the last are some conclusions we have got and the future scope of this research. Firstly, I would like to introduce the background of our research. As an essential subtask for information retrieval, the event detection aims at identifying the event triggers in the text and assign the predefined event types to each of the triggers. And the event types are defined in ACE 2005 corpus, such as attacked, transport, die, and so on. And there is an example. The sentence you can see there, and its event type is attacked, and the blast is its trigger. So as we know, the event detection task is usually modeled as a multi-classification problem in the traditional supervised methods. So it may suffer from the heavy reliance on manual annotations. And in order to overcome this challenge, we model the event detection tasks with some transfer learning approaches. The few-shot learning is the method we use in the paper. Few-shot learning is a typical solution for transfer learning, and its goal is to learn the transport knowledge from training examples, and we call it the sim classes, and to the text example, and the so-called sim classes. And our model is named as Cada Fvae Gan. It is a cross-modal framework, and it using VAE as its key model for future generation. The input of our model consists of three modalities. The first is the event mention structure passed by AMR, and the third one is event type structures, and the last one is some type name embeddings. And inspired by the adversarial training of GAN and its attractive usage in natural language processing, and we follow this, and we follow the generator of GAN and the decoder of VAE into one. So, as is depicted in this picture, a Zeng classifier is able to extract valuable features from latent representations with original modalities and as a model's input, and it will produce acceptable classification results for our AD task. So let's have a look of our proposed model. In our model, you can see three VAEs, one for each modality. And we collapse the decoder in VAE and the generator in GAN into one. And they will share natural network parameters and the training process. And the decoder of VAE does not need to reconstruct low-dimension latent representations. This is a basic foundation. This is basic function of VAE, but it also plays a role of generator in GAN. So in this way, the VAE decoder, the VAE encoder is expected to construct latent features with richer semantic meanings, which is beneficial to the downstream tasks. And the downstream task is multi-classification. Let's have a look at the AMR semantic graph encoder. This is a basic modular in our model. As we know, few-shot learning usually needs high-quality class representations to learn a robust transfer learning model. So we take advantage of AMR to build semantic graph by identifying the event triggers and arguments. And there is an example. In the first sentence, we use AMR to extract its mention structure. You can see in the top of this picture. And the root of this graph is the trigger. And in this sentence, its event type is attacked, and war is its trigger. So war is the root of this graph. And we can use the AMR to generate the type structure of the sentence. And in the type structure, we can see that the event type attacked is the root of this graph, and there are 5 words, 5 keywords in the leaf. The first is attacker, and the second is target. All of these are the arguments of the event type attacked. And the adversary latent feature generating network is a key modular in our model. Our model is named Cada Fvae Gan, and the model itself uses adversary training to strengthen VAE and few-shot learning. This is a basic VAE. In this picture, we can see that the VAE consists of 2 parts. The first part is encoder. The second part is decoder, and in the middle is the latent representations named Zeng. And this function is a loss function of VAE. We can use this loss function to train the VAE. And the decoder is responsible for reconstructing X from the input of the encoder. But we need to do something with the basic VAE, and we propose the cross and distribution allied VAE. As we know, in our few-shot event detection framework, for unseen classes, only category description and few-shot mention samples are provided to training set. Therefore, it is necessary for the model to have the capability of cross-modal generation. Namely, one modality-specific encoder or decoder is expected to encode or decode the another modalities with high quality. For the better performance, we use the beta VAE. Since each modality have its specific VAE, so the final loss of our basic VAE is like this. And by weighting KLD with beta, so we can produce better reconstructions than the trivial VAE. Now, we introduce the constraint to cross-modal reconstructions for every modality-specific VAE, as is depicted in the last picture, and each decoder should learn to reconstruct latent representations for other m-1 modalities, which lead to our cross-allied loss. It's just like this. And the distribution allied for m modality is like this. And Wij is Washington distance between two Gaussian distributions. It looks like this. So we combine the basic VAE loss with the cross and the distribution allied, and we can get our VAEs, and we can get the VAEs, the loss function. It's just like this. So we can weight the cross and distribution allied loss with two factors like this. Now we come to the adversarial training. Our model aims to providing an enlightening perspective to the semantic representations of latent features using a classification task in the NLP field. Intuitively, the high quality of the reconstruction indicates the more interpretable latent representations. So under the constraint of VAE objective function, improving the decoder will accordingly improve encoder. So the laws of generators and discriminators are like this. And we can get the final objective function with the mini and the max gain to training our GAN. So let's come to the experiments results. The first one is application study. This is the results. And in this table, the first one, FGAN is the GAN without cross and distribution allied, and CA FGAN is with cross allied, DA is with distribution allied, and CADA it's without GNN and with cross and distribution allied both. And we can draw the conclusion from the table that both cross-allied and distribution-allied improve the performance. The cross-allied works better than the distribution alignment. And more outstanding results are provided by combining the two tricks. Moreover, introduction of GNN further improves the performance. And the third part of the experiment is model comparison. We show that the proposed few short learning model achieves comparable performance with existing transfer learning framework for event detection. We compare our methods with the following baseline. Uh, the transfer. The transfer model design a transferable architecture for event detection. It used and the transfer use CNN to generate vector representations for the latent mention and the event type structure. And the top 10 most popular event types in AZE 2005 chosen by us is the same with transfer model. So we can see from this table that and that the VAE plus GNN could be used to generate features for event detection tasks in transfer learning situations. And the last part of my presentation is about the conclusion and the future scope of our research. In this work, we propose a few short event detection model named CADA, FGN, GAN, FAVE, GAN, and the model introduces adversarial training to VAE. And to improve the performance of VAE, cross and distribution alignment are used in our work, with cross-aligned latent representations and reconstructions. And the latent representations are enriched by more interpretable semantic meaning. Moreover, adversarial training provided by GAN strengthens the VAE encoder indirectly, and our experiments shows that the transferability of low-dimension latent semantic technology constructed by VAE and the effectiveness of the adversarial training provided by GAN. And the future scope may be focused on zero-shot because our work is based on few-shot learning. We can advance it to zero-shot or generalized few-shot and generalized zero-shot. And this situation is of, and these situations are of more practical value.